Hello, and welcome to question 2, part B. Reminder, question 2, part B is a spring is placed horizontally at the end of a ramp. How far will the spring be compressed if the spring constant is K? Okay, so going back from part A, we have the initial energy of the block is given by EI is equal to mg s sine theta. And also going back to part B, we introduce another term to the final energy of the mass. We have EF is equal to EGF plus ESF EKF. So where EGF is potential energy of gravity, ESF is potential energy of the spring, and EKF is kinetic energy of the mass. When the mass is at the bottom of the ramp and it has compressed the spring all the way at the very end of the compression. So if I were to draw another version where we have the spring has been compressed here, and the blocks over here now. At the very point where the spring is most compressed, the block is not moving. Which means V is 0. So we can plug that into this equation, and also the height of the block is also 0. So that gives us some variables to put into this equation. We have mg0 for final gravitational potential energy. We have 1/2 times k. When the spring is compressed, it is compressed by an amount x of compression, which we don't quite know yet, but we will solve for that. 1/2 kx squared. That's from the expression for potential energy stored in the spring, plus I did double plus right there. Plus 1/2 m0 squared, because the velocity is 0. Because this term and this term both have a 0 in them, we can cross them out, and we are left with 1/2 kx squared. Now, because there is no loss of energy, we have EI is equal to EF. And we can plug in our expressions we have for EI and EF. We have mgs sin theta is equal to 1/2 kx squared. Solving for x squared, we have x squared is equal to 2 mgs sine theta divided by k, and gives us x is equal to square root 2 mgs sine theta divided by k, which is the answer for this question B. Okay, next to part C.